In this video, we're going to start taking a look at the end behavior of rational functions. So I start out here just reminding you what a rational function is. A rational function is a ratio or a fraction of two polynomials. So it's going to have the form p of x over q of x, where p and q are polynomials. So let's suppose I wanted to take a look at the limit as x goes to infinity of 3x squared plus 2x plus 5 over 3 minus 2x squared. Okay, now here's a situation where I've got a lot of individual pieces that are connected by arithmetic, but it's no good evaluating the limit of each piece and then combining the results, because most of these pieces are going to infinity or negative infinity. 3x squared is going to be going to infinity. 2x is going to infinity. Okay, 5 is going to be very happy at 5. 3 is going to 3. Negative 2x squared is going to negative infinity. Infinity plus 5 divided by 3 minus infinity is a mathematical atrocity. Don't go there. We cannot do arithmetic with infinity. Now, I do know, because the top and bottom are polynomials, that they're going to be dominated by their lead terms. So I know that the top is going to behave like 3x squared, so it's going off to infinity, and the bottom's going to behave like negative 2x squared, so it's going to be going off to negative infinity. But even that isn't helpful, because infinity divided by infinity is just as nonsensical as what I said a moment ago. We can't do arithmetic with infinity, because infinity just means that something is big. And things can be really big and get arbitrarily large without being identical in size. X squared and x cubed both go off to infinity. They are not the same size as they do that. X cubed is bigger as it goes off to infinity. So we're going to need to work with this somehow. And here's the strategy. Let me just rewrite this problem here. I'm going to take a look at the biggest power of x that's on the bottom, which is 2. Now, I will eventually explain why I'm concerned about the biggest power on bottom rather than just the biggest power overall or the biggest power on top. Let's make a note. 2 is the biggest power on bottom. I'm going to multiply this thing by 1. Always allowed to multiply by 1. It can change the way things look without changing their value. The form of 1 I'm going to use is going to be the reciprocal of x squared, the reciprocal of x to the biggest power on bottom over itself. Okay. Now, super important. If x was allowed to be 0, this would not be defined. But x is going off to infinity. So this is perfectly fine for end behavior of rational functions. We are not talking right now about limits of rational functions at finite numbers. We already know how to do that. If I'm approaching a finite number, if it's in the domain, I plug it into the function. If it's not in the domain, it's because it makes the bottom 0. If the bottom goes to 0 and the top doesn't, I know it's a vertical asymptote. I do a sign check to see whether we're going to infinity or negative infinity, or if it's a two-sided limit, if the limit doesn't exist because we go off to different signed infinities. If the top and bottom both go to 0, I would try to factor and cancel. So totally different techniques for rational functions approaching a finite number and rational functions going off to infinity or negative infinity. If we are going off to infinity or negative infinity, we know x isn't 0, and so we can use this strategy. Now, of course, what we've got to do then is just distribute this 1 over x squared to each piece on top and bottom. So we'll get the limit as x goes to infinity of 3x squared over x squared plus 2x over x squared plus 5 over x squared all over 3 over x squared minus 2x squared over x squared. Now, with a lot of these pieces, I can do some canceling. So I can say this is the limit as x goes to infinity. Here, the x squareds cancel. That's just 3. Plus here, I can cancel one factor of x, so that's just 2 over x. And here, that piece stays as 5 over x squared. This is going to be 3 over x squared minus 2, because here I can cancel the x squareds. Now, what's great about this is now every piece is approaching something finite. 3 and negative 2 are just finite numbers. All the other pieces have x's on the bottom, and x is getting really, really big, so we know that the reciprocal of a positive power of x is going to be going to 0. So now, instead of having a couple finite pieces and the rest going off to infinity, or negative infinity, I've got a couple of pieces approaching finite non-zero numbers and the rest of the pieces going to 0. Now I can evaluate the limit of each piece and then do the arithmetic. I can say that's 3 plus 0 over 0 minus 2. That's 3 over negative 2, or just negative 3 halves. Okay. So we went from having a bunch of big pieces to a bunch of finite pieces so that we could evaluate the limit. Now, this technique is a great strategy for determining the end behavior of rational functions. I will just show you a shortcut. Now, on exams and quizzes, if I ask you to provide a formal justification, I'm asking to see this work. Formal justification isn't quite the same as formal proof. I'm not asking for you to prove things in terms of epsilons and deltas. Don't panic, okay? But formal justification means show this work, don't use the shortcut that I'm about to show you. But here's the shortcut that I'm about to show you. The top is a polynomial dominated by 3x squared. The bottom is a polynomial dominated by negative 2x squared. This limit is the same as the limit as x goes to infinity of 3x squared over negative 2x squared, which is negative 3 halves. That was fast. Okay. So, if we are going to infinity or negative infinity, and only if we are going to infinity or negative infinity, polynomials are dominated by their lead terms, rational functions are dominated by the fraction of their lead terms. That's a really useful thing to have. When you get to 3b, there are going to be lots of times when you're taking lots of limits, and it's really nice to have a quick shortcut for evaluating certain limits, even if you're ultimately going to show your work. Just for saying, hey, is this a good strategy? Will I get a finite number? You can sort of in your head say, oh, yep, I'm going to get negative 3 halves. Okay. I do expect you to know how to justify that so that you're thinking through this process. So be prepared for that. But if I were to put this question on an exam and just say evaluate the limit without specifying that you need to provide a justification, it would be fine to take this shortcut and just look at the fraction of lead terms.